Lab 6, Magnetic Braking. Introduction and purpose. Faraday's law relates the time-varying magnetic field to a Curry electric field, whose path integral around a closed-loop path is not zero, but provides an EMF that can drive current. This current in turn produces a magnetic field, which exerts a force on the source of the external magnetic field. In this lab, the source of that external field is a falling bar magnet, and the induced current is driven in a tube of aluminum foil. In other words, if you drop a magnet in a tube made of a conductor, it will take more time for the magnet to fall. Procedure. A small bar magnet was dropped in a brand new tube of aluminum foil 5 separate times. A phone was set up to record the test. A video editor app was used to analyze the video for when the magnet entered and exited the tube. The average time was calculated as 0.45 seconds. This is a simple free body diagram for the magnet. This is the data used for the calculations, where we have the mass of the magnet and then the dimensions of the aluminum foil. The fundamental physics principles used in this lab were Faraday's law and Lenz's law. So to help me understand Faraday's law better, I broke down this complicated equation up here into the simpler version down here. Over here on this side, we're going to have the magnetic flux, which is just how much of a magnetic field is in a given area and is represented by phi sub b. And this is going to be how that is changing with time. So a changing magnetic field is going to create an electric field. And if that electric field is in the presence of a conductor, it will create a force that acts on the electrons in that conductor. So as Professor Goldman says, if you kind of blur your eyes, you can see how we can get from here to an induced EMF. Lenz's law says that the induced EMF is such that it opposes the change in magnetic flux that produced it. So we can see in this diagram, if the bar magnet is moving to the right, then if we choose this ring as our observation point, the magnetic field is going to be increasing. So Lenz's law says that the current is going to create a magnetic field that opposes that. So if this magnetic field is wanting to get bigger, the ring says no, and it's going to try to create a magnetic field in the opposite direction. And we can figure that out using the right-hand rule. So this is an animation from GlowScript. And so we can see using the same diagram that the red, viewed from the top, represents counterclockwise current. This is the graph of the velocity versus time for the falling magnet. So if we look at our simple free body diagram, where we have our magnetic force acting up and gravity down, and we assume that the force and gravity is constant, then the sum of these forces is going to be the difference, and that's going to be equal to the mass times the acceleration. So looking at the graph, we can see at the beginning we have the steeper curve, and we know that the derivative of velocity is going to be acceleration. So in the beginning we have a steeper or a greater acceleration, so we know that we're going to have a greater difference. And gravity is constant, which means that the magnetic force has to be smaller. And that makes sense because from Faraday's law we can say that we only get this magnetic force if the flux is changing, which means that it has to be moving. So if it's starting from rest, it makes sense that this magnetic force is going to be smaller at first. What if the resistivity of the conductor were reduced as close as possible to zero? How would that affect the dynamics of the falling magnet? From Ohm's law we can see if the resistance is going down, the current's going up. Then using this equation, we can see that if the current's going up, the magnetic field is going up. So we can say current goes up, magnetic field increases, the difference between the magnetic and gravitational force decreases, the magnitude of the acceleration decreases, therefore the magnitude of the velocity changes more slowly. What if holes or slots were cut into the tube? How will this affect the ring currents in your model? So using this equation, this form for Faraday's law, where this is for a coil, N is the number of turns in a coil, but we represent that as just the number of rings. So the holes or slots could be thought of as gaps between the rings, but the model is still going to have the same length. So the number of rings in must go down. EMF goes down, current goes down, magnetic field decreases. The difference between the magnetic and gravitational force increases. The magnitude of the acceleration increases. Therefore, the magnitude of the velocity is going to be changing faster. In conclusion, using the kinematic equation for an object falling from rest to calculate a time of 0.305 seconds. The average time falling through the tube was greater than that, which makes sense because gravity was not the only force acting on the magnet. Another interesting fact I observed was that if we combine the magnets, they feel slower than a smaller, lighter magnet.